Alright guys, this video is on Maxwell-Boltzmann distribution. You might have seen it on some of the Boltzmann videos that we were watching earlier in the unit. So what this is basically you have on your y-axis number of particles that could also be number of molecules that are present there. On your x-axis, it'll have molecular speed, and this whole distribution correlates with the idea that temperature and the average kinetic energy are proportional to one another. So what that means is that if I have these molecules moving around fairly quickly, then that kinetic energy is higher. So the faster the speed is, the faster the kinetic energy. That correlates because of the kinetic energy equation. Kinetic energy equals 1/2 mass times velocity squared. Now the difference between velocity and speed is a scalar quantity, so it's only looking at magnitude. Velocity is a vector quantity, which means that it's looking at magnitude and direction. We're not really worried about the physics of that, we're just worried about the magnitude, how fast they're moving. So if I have these molecules that are the same mass and they're moving at a faster speed, that means that they have a greater kinetic energy. And because kinetic energy is proportional to temperature, if I increase the kinetic energy of some molecule, then that means that the temperature of that molecule increases as well. So this is the big concept that you have here. Now, also, if I have substances that have the same kinetic energy, I can look at the relationship between mass and velocity. If mass increases, then that means my speed, my velocity, will decrease. The opposite is also true. All right, this is like saying, hey, heavier things move slower. Okay, more massive things move slower. So there's really two main ideas, two questions that they ask with these Maxwell-Boltzmann distributions, and they mostly show up on multiple choice. So the first one is, if you have particles that are the same molar mass, so same molar mass. So you have this, you're dealing with the same particle, or you have two different things that have the same molar mass, then what it's looking at is the relationship between the speed and the temperature. Speed and temperature. So conceptually, we now know that if I increase the speed of something, then that consequently increases the temperature of those particles. The second main question, the second main idea you have to look at from these Maxwell-Boltzmann distributions is if they have the same kinetic energy. So same kinetic energy, this can also be correlated with the same temperature because we know that they are proportional to one another. So if they're the same kinetic energy or temperature, then what they're going to look at is the relationship between speed and molar mass. Conceptually, we know that if molar mass increases, our speed decreases. So now let's take these ideas of the questions they like to ask and actually apply it to the Maxwell-Boltzmann distribution. Now, you will not have the luxury of actually seeing these temperatures. Instead, you'll just be given the graph with the particular lines. Okay? So I hope none of you guys are colorblind, but if you are, this line that you see right here, I'm going to call red. This line here, I'm going to call pink. This line here, I'm going to call blue. And this one that has the highest little peak here, I'm going to call that one teal. Okay? So let's talk about our first question. Let's say that all four of these lines are dealing with the same particle, the same molecules. Let's say they're all oxygen. Okay, so you have oxygen molecules all right here. So what we want to know is which one of these lines is at the highest temperature, or which one of these lines are at the lowest temperature. Conceptually, as speed increases, my temperature increases. So if I want to look for the highest temperature out of these lines, I want to look for the line that has the greatest speed. Now, when I'm looking at that, I'm not looking at my peaks. I'm not looking at my height of the peaks. What I'm actually looking at is the area under the curve. So if I look at the area under the curve of all of these, all right, another way you can look at it is look to see where this peak lies on the x-axis. So the red peak lies right there on the x-axis. The pink one, the pink or purple, whatever you see right there, that is going to lie right there on the x-axis. The blue one is going to be right there. And the teal one is going to lie right there on the x-axis. Technically, I'm looking at the area under the curve. I don't know if you guys have actually gotten into that with math or not. I think it's a pre-calc concept. But if I look here, then I will notice that the red line has the greatest molecular speed. So how that translates is the red line has the greatest temperature. Now let's look to see who has the lowest temperature. Well, this one right here lies on the x-axis right here. So it has the lowest molecular speed. Since it has the lowest molecular speed, that means it is the lowest temperature. So that's how you go about answering the first type of question right there. Now for the second type of question, it says, well, let's say that all of these lines are different molecules or different particles. Let's figure out what each one is. Well, conceptually here is that as speed decreases, my molar mass increases. So let's say I was just looking at this red line and just looking at this teal line. And one of these is oxygen, O2, and another one is H2. And I had to identify which line is which. Conceptually, what I'll do is look where the peak is on the x-axis. Look where the peak is on the x-axis. What I see here is that the speed of the red line is greater than the speed of my teal line. And we also know that lighter things move faster. So this red line is probably H2 because H2 has a smaller molar mass than O2. This teal line could potentially be O2 because O2 has a greater molar mass than H2. Therefore, it will have a slower speed. So these are the two types of questions that they love to ask. Super simple as long as you know how to read your graph correctly. Now remember, it's not the height of the peak that we're working with there. It's technically the area under the curve. So I hope that helps you out a little bit.